A very good afternoon and warm welcome to one and all the attendees of this live session. I am Dr. Vaibhav Pandit, and today we are going to discuss the topic from the subject image processing, and the topic here it is titled that it is spatial filtering for image restoration here. So already we are covered with the 7 live sessions associated to this particular subject image processing. So with the formation of image, the representation into it a digital format here, and then further processing we have been learning so far. So various fundamental steps associated to image processing, those we have already learned. Image restoration is one of the popular step and very essential for digital image processing. So we are going to focus the spatial filtering part of the image restoration here. So associated to this particular topic, as far as your examinations are concerned, I will directly come to the form of the question that is usually asked thereupon. So the question is usually of the form, what are the spatial filters for image restoration in the presence of noise only condition here, or sometimes it is also referred to as additive noise only condition. The noise is of additive type here. So this question I am taking, which is going to cover the entire spatial filtering for the image restoration. Sometimes the questions may be as such, they are limited to a specific portion of the spatial filtering as well. So that will of course be covered in such a question. What are the spatial filters for image restoration in the presence of noise only condition? So I must get you clear that we have to provide the details of the 3 types of the spatial filters for this particular task, and these 3 filters are mean filters, order statistic filters, and then lastly the adaptive filters here. Rest of the filters, those you encounter while learning the image restoration, are of course the filtering processes, but they take the help of transformation from spatial domain to the frequency domain, most popularly by the use of Fourier transformation. And those filtering processes we can categorize as the frequency domain filterings. Again, the intention is the same, to achieve the image restoration here. So these are the filters, those work into the plane of the image only. That is why we term them spatial filtering here. So very first one, that it will be the mean filter. We shall first of all go into the details for mean filters, then the the order statistic filters, and lastly the adaptive filters here. So before beginning with the details of the mean filters, the title is also the self-explanatory. We shall see what is the noise only condition with regard to which the question has been generated here. So noise only condition is to be considered for the image restoration process. In our previous live session, we have discussed about the model of image degradation oblique image restoration process. I hope you can remember it, the very simple model, or you can get back to that video as well here. So whatever the input or the original image was supposed to be first of all degraded, and then further the noise was getting added, and then the image restoration process. The block diagram, it is there. I am again going to recall that particular diagram here. Just focus on to the mathematical expression where we were intended to see the characteristics into the resultant images after degradation. Those are represented into the spatial domain by g as a function of x comma y, into the frequency domain denoted by capital G as a function of u comma v here. So f of x comma y, this was the original image. This is the first representation into the spatial domain. So f of x comma y is the original image. So it is added by certain amount of the noise. Along with the f of xy was operated by the degradation function, most possibly represented by the convolution operation with h, the function in the spatial domain here. So as we are talking about noise only condition, there it is the presence of noise only, not the other type of the degradation, no motion blur or certain another kind of the blurring there it is. So this is what the same condition, but representation into first of all the spatial domain and then the frequency domain. So whenever we are learning the spatial domain filtering, we have to refer the first equation instead of the second equation for this particular topic here. So as we see here, the goal of image restoration is to get back whatever the information there it was into the original image, recovered, restored in the efficient manner here, or sometimes we also expect to get that information enhanced. So this is what the intention of having the image processing for any of the information present into the two-dimensional form, where we can plot as the image, digital image here. So here the best option you can see that if we can subtract the second part onto the right hand side, which is representing the noise part. But as the noise part is totally unknown, it is basically most of the times a random signal, so it will not be feasible to just subtract the noise component from the image that we are working with and get back the original details. So the best option is to go for the spatial type of the filtering here. So here in terms of the words, we are focusing for g of xy or into the frequency domain g of u comma v. So subtraction is not the realistic solution here. That is why we are going to opt the spatial filtering, and this is why we go with the mean filters or the statistic filters, and then finally the adaptive type of the filters. Now we were discussing about the noise only condition or the additive noise only condition. So I get back you to the block diagram. So it is not at all necessary to draw the block diagram in the answer for this particular question, but it is into the background where we have learned the complete model, the complete image degradation and then the restoration process here. So in this block diagram, your original image before degradation, here it is represented onto the left hand side. So generally what happens, it is fed as input to the first block where the degradation filter function, here it is the mention of capital H. So it is basically into the frequency domain. In the spatial domain we will be using small h. So the convolution of the image f with the filter function h is supposed to be first of all done. That process we are supposed to cancel. We don't expect any kind of the degradation that has been associated to the original image with the help of the degradation function. We directly take f of x comma y added by the noise. Here the noise, some textbooks referred it by eta as a function of x comma y and some n as a function of x comma y. X and y are just the spatial dimension representations here. So that time we obtain such an image which holds the original information from the image f of x comma y and the noise. Our intention is to get back the details into the restored form. So what kind of restoration filters we are going to apply to get back the details? The filters are of the spatial type and I have already listed out them. Those are the mean filters, order statistic filters, and finally the adaptive type of the filters. So associated to this particular block diagram, we are again having the mathematical notations into the simple form, how we have only the noise added to the original information. So eta as a function of x comma y is added to f of x comma y. Here it is no convolution with the degradation function. That is why we have put a cross mark onto the first block of this particular image degradation oblique image restoration model here. Now we shall enter the details of the first filtering, that it is mean filtering here. So for mean filtering, what is mean? Mean is nothing but the average here. So mathematically we express the two types of the mean. First one is the arithmetic mean, where we represent the output by f cap as a function of x comma y obtained by 1 upon mn, summation where the parameters s and t belongs to capital X suffix x comma y, which is the local neighborhood, and this summation is operated over g as a function of s comma t, the representation of the image before finding the averaging or the mean here. Now this local neighborhood that I have represented here by the capital S suffix x comma y is nothing but the representation of a window. So this window will be centered at the pixel location provided x comma y here. So this is one kind of the mean we can represent mathematically, that we mostly refer to as arithmetic mean here. Along with this, we have the second type that we refer to as geometric mean. So the output of carrying out the geometric mean over image as a signal, a two-dimensional signal, we can express like this. So here we can represent f cap as a function of x comma y obtained by the square bracket that holds the power 1 upon mn. So here we are having a pi function. Again, s comma t belong to the neighborhood, or rather you call a window, capital S suffix xy operated over g as a function of s comma t, the degraded image under consideration we can see here. Now the effect of these two types of the means here, the arithmetic mean and geometric mean, as usually we have the original image to represent here. The first block on the left hand upper side here, the original image can be better seen for comparative purpose in this particular diagram. So here on the right hand side, the upper block, we have the resultant of noisy Gaussian with mu representing the mean equal to 0 and sigma representing the standard deviation equal to 20, which can lead to the variance as well, to represent by sigma square. So basically into your examination, it is not at all necessary to draw, and it is even difficult to draw the images, what kind of output we are generating when we implement the mathematical equation, those just now we have seen, into any of the image processing software, and we process the original image by these particular averaging functions. So we can obtain the output images here, just to show you the different effects into the output images as we change the type of the filtering. Here we are going to see. So the first image is just the noisy Gaussian image. See, to the original image we have added the noise to it. So this is what the original image, you can see there is no noise here, and our intention is to get back the same details into the restored image. So we first of all add noise to it, that is of the Gaussian type. Mean is equal to 0, the standard deviation sigma is equal to 20 here, and when we apply the first type of the filtering, arithmetic the arithmetic mean here, so we obtain this particular resultant image that is shown on the left hand side downwards here, whereas the resultant of the geometric mean is shown here onto the right hand side downwards here. So now you can compare both of the results. The encircling of a simple portion from this image for the same location in both of the resultant images has been represented here just for the comparative purpose. Here you can see the effect of different mean filterings onto the original images here. So depending on the performance, it is quite helpful to select the special type of the filter so that it suits the application here. Now after the arithmetic mean and the geometric mean, there it is another popular type of the mean filtering which is known by harmonic mean filtering here. So in the harmonic mean filter, the output filtered image, I say that usually we are representing as f cap as a function of x comma y, is obtained by, here we express again in mathematical terms, so m by n divided by the summation s comma t belonging to capital S suffix xy, the window, it is focusing the pixel here at the center location. So it is operated over 1 upon g as a function of s comma t here. After harmonic mean filter, we have the last type of the mean filter, that it is popular and somewhat the modified form of the harmonic filtering here, that is known by the name contra harmonic mean filter. Here it is the mathematical expression how we can obtain the output of contra harmonic mean filter. So f cap of x comma y, it is obtained by the numerator here the summation operation over g as a function of s comma t to the power we have capital Q plus 1. In the denominator we again have the summation operation over g as a function of s comma t, where the power is capital Q only. So capital Q is a new thing in the representation up till now as we have gone through. So it is nothing but just a coefficient here, or a quotient we can generally see to get it by the letter capital Q here. We can vary the values. We can either, so this equation just modifies to the earlier representation, that is of the harmonic case here, and we can also apply the positive values to this particular quotient, so that we can have the various forms by variation. The flexible type of the mean filter here we are having, that is contra harmonic mean filter here. Now again we get back to the example just for understanding purpose. So most possibly the image is added with the noise here. The noise are of different kinds here. In our previous session we have discussed the 6 types of the noise models, right from the Gaussian to the salt and pepper noise. Salt and pepper noise is most of the times also referred to by the name bipolar noise as well here. And if you take only one form, you can call it to be the unipolar noise here. So when we have the image, original image added by the unipolar noise, let us say the pepper noise, and in the next case we have the salt noise. You can see on the left hand side the most of the image portion is affected by the black dots. So this is just like the paper here. When we are representing the image intensity, the pixel intensity from 0 to 255, so into the 8-bit environment, when you put 2 to the power 8, you get 256 possibilities of gray level or the intensity levels here. So most of the pixels are intentionally made to the dark dots to represent the lowest possible intensity level, that it is 0 here. So this is nothing but the paper noise. And when you see the white dots into the same image, this is nothing but the salt noise here. So now with the help of the image restoration process, we will like to have reduction into the noise here. So for that purpose, when we use the contra harmonic mean filtering, putting capital Q value to be the positive 1.5, you can get a clear picture which is very similar to that of the original image. So I can say this is the successful spatial filtering for obtaining the image restoration. So this is for the paper noise. Here it was the input image, and here we have obtained the output image. Now for the second, that is it on the right hand side, the image affected by the salt noise, when we change just the sign of the contra harmonic, the quotient representing the Q here, magnitude we keep to 1.5 again. So Q is equal to minus 1.5. So this time we obtain again one image which is very similar to that of the original image, and which has reduced the salt noise to a great extent here. So this is what the use of the contra harmonic mean filtering here. When we mistakenly get change with the notations or the values from positive to negative, from negative to positives here, so there it is a wrong sign. So wrong sign into the contra harmonic filtering will lead to losses into the image information as well. So I hope you remember the original image here. When we just swap the signs for the contra harmonic filters with Q is equal to the magnitude 1.5 here, see the corresponding resultants of the paper noise and that of the salt noisy image are represented here. So here we have selected Q is equal to minus 1.5, and here it is Q is equal to 1.5. So the image that was affected by paper noise, instead of reducing the paper noise, this image is filled with more paper noise, more darkness of the pixels has been increased in this particular image, whereas you can see more white spots for the corresponding pixels you can see. So the salt noise has been increased into the image that was originally affected by the salt noise. So when you mistakenly change the signs or put up the wrong coefficients at that particular place into the mathematical expression, you can also get the wrong results. Those are totally not desired here. So the selection of the value q should be very specific to look at the application at hand. So here is one student, G.I. Raja. Sir, mera naam lo. So if you have any query, you can ask me, rather I can continue my topic. So I hope we are finished with the understanding of the four types of the mean filters. The first one, the arithmetic, the geometric, then the harmonic and the contra harmonic filter here. After that we shall focus our attention to the order statistic filters here. See, order statistic filter is very popular in the spatial domain filtering here. So individually the question may also focus on to the only order statistic filters. So that time you have to give the details of the same, not the mean filters. So as you see the name of this particular filter, you see the first term that it is order. So order, you know, the ascending order, descending order. So forming a sequence with a specific criteria of either increasing into the magnitude or decreasing into the magnitude, that it is nothing but the ordering here. So along with the ordering, here it is the statistics. So some statistics is worked out for the order of the pixel intensities, and this kind of filtering is nothing but the order statistic filtering. So I have already made it clear these belong to the spatial domain here. The response is based on the order, which is also known by the ranking here. So now the response of this particular filter at any certain point can be determined by the ordering or the ranking result only, hence this is the name. And this type of the order statistic filtering is the best suitable for the unipolar or a bipolar noise that just now we have dealt with, which is also known by the name salt and paper noise here. Now there are subtypes to the order statistic filtering. So here we are having the four subcategories. So the very popular under this order statistic is the median type of the filtering here, and next to the median filtering we have the max mean filtering, next to that we have midpoint filtering, and lastly the alpha trimmed mean filtering here. So one by one we shall go into the details of all these four filters. Just have a clarity in your concept that all these four types of the filters are working onto the certain criteria of ordering the pixel intensities and finding out the resultant image pixel intensity by the statistics here. So let us have the details of the first type of the filter, that it is the median type of the filter. So median filter, I hope the title is very self-explanatory. We have to find the median here. See, this is the best known filter from the subcategory of the order statistic filters here. So as we were discussing, the median, the name implies that the value of the intensity of that particular pixel we have to replace. We have to replace by first of all measuring the median of the gray levels or the intensity levels of the neighboring pixels, the pixels in the neighborhood of the pixel under consideration here. So how to find the median? So determining the median can simply be mathematically expressed by this particular step. Here the output image. So output image we can generally call it to be the filtered image represented as f cap as a function of x over y. So this can be obtained by finding out the median for the local neighborhood that is represented capital S suffix xy, for which the median is performed onto the entire image represented g as a function of s comma t here. So the thing is simple. The original value of the pixel we have to consider into the neighborhood, find out the median and replace the central pixel value by whatever the median value we get as the result here. Now the popularity of the median filters is really a question here. We have the max min filters, median point filters, then the alpha tree mean filters also. Thing is very clear, as it is giving us most of the time precise results with less efforts. That is why this particular filtering is popular here. So the reason we can say that for certain types of the random noise, it is providing the excellent noise reduction capabilities with considerably less blurring than the linear smoothing filters of the similar size here. That is why it is popular and particularly effective in the presence of both the bipolar and unipolar impulse noise as well. So now we take one simple example where we shall be performing the median type of the filtering here. So for median type of the filtering, here we are selecting one example image plane here. So in this example image plane, you can see here we have 1, 2, 3, 4, 5 and 6 rows and the 6 corresponding columns here. So we have 6 rows and 6 corresponding columns. So we can represent that is 6 by 6, total 36 pixels here we have. So now when we are considering the 8-bit environment here, so as we see particular noise by the use of median filtering. So as we are focusing on to the pixel with the intensity as denoted 255, we have to consider such a neighborhood. So a neighborhood we are selecting of the dimensions 3 by 3 here. So one neighbor we have taken on upward sides, that is representing the pixel intensity of 83, one on the downwards, that it is representing 221, one on the left hand side with the pixel intensity 94, then next on hand side with the pixel intensity 94, then next on to the right hand side with the 215, then the diagonal corners of this neighborhood we are representing. We have 137, 189, we have 179, we have 200 as well. So now we have total 9 pixel intensities at hand when we apply the neighborhood of the dimensions 3 by 3. So at this point what we need to do, we just need to order the pixel intensities, and here for median filtering we shall be working with the ascending order. Either you go for the ascending order or descending order, the median it will be the same. So for ascending order we arrange the pixel intensities from smaller to the larger values here. So out of the 9 pixel intensities, the first one that will be 83, next it will be 94, then 137, 179, 189, 200, 215, then we have 221, 255. So what you need to do, you have to strike out each entry from left hand side and right hand side. Go on. So as the neighborhood you have selected 3 by 3, total 9 pixel intensities you get, that it is the odd number. So as you strike out the entries into this ascending order from both the ends, there it will be left with the middle value. It is nothing but the median value. So as here it is the value 189, so the 255 that it is represented at the center, we have to replace with 189. So when we do this, so at this time you see the replacement of the value we have done. Rest of the neighborhood pixel intensities are as it is. So this is what the output image which is obtained by operating with the median type of the filtering here. Now we extend this particular problem for the another type of the noise. Here we have the complete whiteness by the representation of the pixel intensity by 255 when we have 0 instead of the 255. So Again, take the same image pixel sample here, and at the pixel under consideration where we have the center of the neighborhood here, here we represent the pixel intensity by 0 here. So when we have to obtain the resultant image by determining the median, so that time we again go for the ascending order, and as we have the central frequency value intensity value to be equal to 0, for ascending order we have to start at 0, then 83, then 94, 137, 179, 189, 200, 215, 221. So if you compare the ascending order that I have just made here and to the previous one, you will come to see we started at 83, we ended at 255, but here it is no 255, instead here it is 0. So that is on the another hand. So when we strike out each and every entry equally from both the ends, you will get to the value left, that it is 179. So at this particular image sample, this will be the resultant pixel intensity, which is to be substituted in place of the 0, as we see the center of this particular neighborhood here. So here we display the resultant image sample by obtaining the median filtering here. So what we have actually done, we can summarize the points here. So the center values of the 3 by 3 pixels into the original image we have replaced by the median value. So this point should be very much important while performing this particular filtering here. The median filter technique is applied for each of the non-overlapping block of 3 by 3 pixels from top left to the top right corner and from top to bottom. Always remember that for any of the image sample, the top left corner is the origin here from where the filtering is supposed to get started here. Now while performing the median filtering, there are certain situations when we have the pixel intensity under consideration that is originally located at the either a corner or somewhat a border here. So let us have a look on all these particular situations. We have the 3 cases. Let us see the first case. So here the computational block overlay only the pixels that are into the original image. So the neighborhood is not going outside the dimension of the image here. So next one is the computational block overlap pixels the outside the original image, but the center pixel overlaps the pixels into the image. So the central pixel is originally relying into the image here, but as we are going to focus on to the neighborhood with a symmetric dimension here, so these 3 pixels are referring to the values those are outside the image information. So most of the time 0 padding is considered as a solution to this situation here. And there it is another situation, we have the computational block overlap is only the center pixel is outside the image. So this is the rare case to occur in the median type of the filtering here. Now we shall see the effect of the median type of the filtering onto the image under consideration that we are usually carrying out for this particular topic of image restoration. So let us have the first image to be affected by the pepper and salt noise here. The density of this particular noise is 0.2 here. When we apply the median type of the filtering for the neighborhood of the dimension or the template you say or the mask you say, that is of the size 3 by 3 here. So here it is the result onto the right hand side. You see a clear picture. Now when we have the repeated median filtering, so you get the corresponding results in the downwards row here. So the repetition processes of the median filtering will be the best solution to reduce the noise of the type, that is the salt and pepper noise. But there is one disadvantage as well. The disadvantage is that the repeated processing by the median filtering will lead to the blurring here. So the blur is again a kind of loss here. So this was all about with the first type of the order statistic filter that you can refer to as 2.1 as well. Now we shall have the details of the second subcategory under the order statistic filters, that it is max and mean filters. From the name you can guess what we shall be doing while we have the ordering of the pixel intensities. So here we shall be focusing determining the maximum and the minimum here. So although the popular technique we are just now covered, that is of the median type of the filtering here, so sometimes it is also required to just find out the maximum and the minimum here. So this is what the filter here we have. So the median represent the 50% of the ranked set of the numbers, but from the basic statistics the ranking tends itself to many another possibilities, and the maximum and minimum are such possibilities we are going to deal with. The example we can discuss where the 100% of the results into the so-called maximum filter we can mathematically express by this particular expression, where we obtain f cap as a function of x comma y. Here on the right hand side we represent the max function, determination of the maximum pixel intensity out of the neighborhood. The neighborhood here it is represented by capital S suffix x comma y. So the neighborhood already we have shown while solving the simple problems associated to the median type of the filtering here. So this is what the filter, it will be the max filter. It is quite useful for finding the brightest point into the image plane here. And since we have the images affected by the paper type of the noise, it has the very low values here, so it is reduced by this particular filter as a result of the maximum selection processes into the sub image area that we are representing by the neighborhood here. So this way also we can make the use of the max filter to reduce the paper type of the noise here. Now when we take the 0% of the filter, then that time this particular type of the order statistic filter becomes a minimum filter here, what we can call as a minimum filter, and mathematically expressed by the relation where we obtain the filtered image represented by f cap as a function of x comma y, it is equal to minimum function operated over the entire image g as a function of s comma t, and this operation is performed by changing the position of the mask or the neighborhood of the dimension s as a function of x comma y here we can say. So the usefulness of this particular minimum filter is quite opposite to that of the earlier, that is max filter here. So this will be helpful for finding out the darkest point into the images here. So it also reduces the opposite type of the noise to that of the paper noise, which is the salt type of the noise. So the salt type of the noise can be reduced by the use of minimum filtering here. Now let us see the effect of the maximum and minimum filtering onto the image affected by the paper noise and that of the salt noise here. So here we take the two images. Here it is the first image which is affected by the paper noise having the density 0.2 here. Here it is the image affected by the salt noise with the density 0.2 here. When we filter these two images from the maximum filter and then the minimum filter here, the corresponding results you can see here. So this way you can obtain the reduction into the salt and paper noise by the individual use of the max and mean filters here. Now in the category of order statistic filters, we are covered with the median filter, then we are also covered with the max min filter. Now the third one is the midpoint filter. You can judge what can be there in this particular filter, but the question is how this particular filter is different than that of the median filter and the earlier one max min filter here. So here we have to carry a simple computation where the midpoint between the maximum and minimum values into the area composed by the filter. So here we have the mathematical expression to describe the same. The resultant image is f cap as a function of x comma y. So this can be obtained by 1 by 2. In the square bracket we represent the max operation, and it is added to the term that is of mean operation here. So this filter is basically the combination of the order statistic filtering and that of the averaging filtering, what we have already termed out to be the mean filtering here. So this particular filter best works with the randomly distributed noise, and this is like the Gaussian and the uniform noise here. So after covering the midpoint filter, the very simple one, the combination of the earlier two here, we have the last category for the order statistic filters, that it is the alpha trimmed mean filter here. So alpha trim is the new term that has been added to the family of the spatial type of the filtering to achieve the image restoration here. So the information with respect to the alpha trim mean filter can be given such a way. So if we can discard or if we can delete the half, that is d by 2 lowest and d by 2 highest gray level values of the image under consideration, denoted by g as a function of s comma t, applying a certain local neighborhood. So that time we can imagine that, we can assume that g suffix r as a function of s comma t represent the remaining mn minus d pixels here. So whatever the output we get, so we can say a filter that is formed by averaging these remaining pixels is called as the alpha trimmed mean filter. So you have to focus on to the word that is trim here. So trim, here we have to set a label and we have to discard few of the things with respect to that defined label here. Mathematically here we express the alpha trimmed mean filter by f cap as a function of x comma y obtained by 1 upon mn minus d. The summation here we have for gr as a function of s comma t, which is the middle of the mn minus d pixels here. So the value of d, so d is the threshold value we have to set. So that can range from 0 to mn minus 1. So the entire range we can go for, and different possibilities here we can go. When we select d is equal to the first value, that is equal to 0, so the alpha trimmed filter will nothing but the arithmetic mean filter that already we have seen. Now if we select the value of d to be the midpoint, so 0 to mn minus 1, the entire range here we have, and if we select mn minus 1 divided by 2 here, so this will be nothing but the median filter, the first type of the order statistic filter we have discussed before. So for all the other values of the d we can set in this particular range, the alpha trimmed filter is useful in the situations involving the multiple types of the noise, such as a combination of salt and pepper and a Gaussian type of the noise here. Now let us have the simple example to see the visual effects of this type of filtering onto the original image, which is further added by the noise here. As the question, you must remember the question that it was, what are the spatial filters for the image restoration in the presence of noise only condition or additive noise only condition. We are not considering the degradation effect because of the degradation filter function, but we are considering only the addition of noise to that of the original image here. So let us have the uniform noise added to the image with the mean equal to 0, the variance represented by 800 here. So when the image is further corrupted by the pepper and salt type of the noise, so the dark and the complete white noise spots when added to the earlier noisy image, so this is what the result we see in the second block. Then for such images when we apply the filterings. So first of all, let us have the filtering performed by the 5 by 5 size of the neighborhood applied for the arithmetic type of the mean filtering here. So 5 by 5 total 25 entries will be there, and for that one we have to determine the arithmetic average here, and final pixel intensity can be selected this way. You can see a kind of blur on this particular output as well. When we filter the image by the use of again the same 5 by 5 dimension of the neighborhood, but the type of the mean filter is the geometric mean filter. Here it is the corresponding result you see in the middle row on the right hand side. Next to that, when we have the filtering by 5 by 5 dimension median filtering, you can see quite pleasing visualization of the image information. And next, the last category of the filtering of the order statistic type, that is alpha trimmed filtering. Here the mean filtering alpha trim type here we have selected, where d value was set equal to 5 here. So this way we are covered with the first type, that is mean filtering. So for mean filtering, the subcategories we have learned, those are arithmetic mean, then geometric mean filter, harmonic mean filter, then contra harmonic mean filter. After this mean filtering, we had the order statistic filtering. So for order statistic filtering, the subcategories were again the four. Those were median filters, max mean filters, midpoint filters, alpha trimmed mean filters here. So after these two categories having four subcategories, we have the last type, that it is the adaptive filter. It is quite complex as compared to the earlier ones, but a very popular one. So let us see the details of adaptive filters here. So once selected the filters, the previous type as we have discussed, applied to an image without the regard of how the image characteristics vary from one point to another. The adaptive filters are whose behavior changes based on the statistical characterization of the image inside the filter region defined by the m by n dimension, having the rectangular window defined represented capital S suffix x comma y. So thus this is capable of having a comparative performance superiority with respect to the earlier filters here. So as you compare the adaptive type of the filter with the earlier types, the thing is very simple. The earlier filters are not at all considering any of the behavior of the noise or that of the image information into the original signal here, and they have a predefined way of operating to obtain the output or the resultant image intensities here. We can say here the working of the filtering for the adaptive type is changing. These changes are according to the image characteristic affected by the noise, of course, here as we are discussing the condition of additive noise only. So that is why the name to this type of the filters, the adaptive filters here. So one very important point with respect to the filtering processes, the structuring of the filtering processes, we can say that when you intend to have improved performance, the practical observation is that the complexity is increased. So more complex designs give you the more good performance of the filtering here. So for that purpose, the time consumption and rest of the resources are also consumed. So depending on the application, the type of the filtering must be selected here. Now as we have for the mean type of the filtering the four subcategories, for the order statistic filtering we have again the four subcategories. For the adaptive type, here we have the two for image restoration process. So the first one is adaptive local noise reduction filter, and the second one is adaptive median filter. So first of all we shall focus on adaptive local noise reduction filter here. So here we have the simplest statistical measures of a random variable that most of the times we have referred to. Those are the mean value and the variance value we can compute. So these are the reasonable parameters on which to base an adaptive filter, because they are the quantities very closely related to the appearance of the image. So whatever the image information we have hidden into the signal, so that can be better explained by the statistical measurements of the mean and variance, and both these parameters are made into the consideration before finding out the resultant pixel intensity here. So here the mean filter gives the measure of the average gray level in the region over which the mean is computed, and the variance gives a measure of the average contrast into the region. So this way these two parameters are very helpful in the filtering process here. Now as we have these two parameters to be the known for this type of the adaptive filtering here, so these are known initially for the local neighborhood that we define by and represent by capital S suffix xy here. So when we get the output of this particular type of the filtering, that we call the response of the filter at any of the pixel location defined by x comma y on which the region is centered. So we have the four quantities based on to which we have this particular output. These are, first one, g as a function of x comma y. This is what the input image we are considering for this type of the filtering. So this is the noisy image pixel value. So g is the value and xy is its location into the image plane here. Next to that we have sigma square, the suffix n. So this is the variance of the noise. So we assume a known prior parameter like this here. Then we consider a local mean represented by m suffix l, and then the another type of the variance at the local. So here it is represented sigma square suffix capital L here. So here we expect the behavior of the filter in few of the steps. The three steps I am going to summarize here. The first step is, if the noise variance is equal to 0, the filter should return simply the value of g of x comma y. So this is called as the zero noise case, in which g of x comma y is equal to f of x comma y. Secondly, if we compare the two variances, one for the local neighborhood and another for the noise here, and when we have the variance of the local greater than that of the noise, it is expected to return the value that is very close to g of x comma y. So here, in other words, we can say a high local variance typically associated with edges, and this should be preserved here. And when we have both these parameters to be equal, so it has to return the arithmetic mean represented by ml here. So the mathematical expression, or you can say formula, to describe the operation for the adaptive local noise reduction filter can be given here. So f cap as a function of x comma y, it is equal to g of x comma y minus the ratio of the two variances multiplied to the square bracket that holds the subtraction of the local mean from g of x comma y. So because of this, the only quantity that needs to be known or estimated is the variance of the overall noise here. So that is very important here. And there it is another parameter also computed from the pixels of the local region here. So the each location defined by x comma y for which the filter window is centered and is to be shifted from the origin, that is the left upper corner to the right upper corner, and from upper to downwards here, from top to downwards here. Now see the effect of this type of filtering onto the noise affected images. So initially we consider the noise of the Gaussian type present into the image with mean is equal to 0 and the variance is equal to 1000. Applying the arithmetic mean filtering of the 7 by 7 neighborhood dimension here, this is what the output resultant image of the filtering on the right hand side top row here. Whereas the geometric mean filtering with the same dimension of the neighborhood, here it is represented downwards, the first entry. And when we have the adaptive type of the filtering, you see the result here. So as these are the two regions encircled, to compare the performance of the adaptive filters with the earlier, that is the arithmetic mean and the geometric mean. So this particular portion is very much clear, whereas this portion is blurred into the resultant images obtained from the arithmetic and that of the geometric type here, whereas the lines for this particular structure are also very clear, where it is quite difficult to judge them into the resultant images from the corresponding arithmetic mean and that of the geometric type of the mean filtering here. Now the last topic we are going to discuss, which is a second subcategory of the adaptive type of the filtering, another popular one, that is called as the adaptive median filtering here. Adaptive median filtering here. So as we have adaptiveness as well as the medianness here. So a simple median filter that performs well as long as the spatial density of the impulse noise is not large here. The adaptive median filter can handle the impulse noise with probabilities even larger than it. So the additional benefit of the adaptive as well as the median type, we are getting the preservance of the details. The details means the information content of the image, while smoothing the non-impulse noise, and sometimes that the traditional median filter does not do. So here the performance of the popular median filter, a subtype of the order statistic filter, has been improved by having the addition of adaptive characteristic to the filtering process here. Now the comparison to the earlier other filters we can also do, where we can make a remark that unlike the earlier filters, however the adaptive median filter changes the size of the neighborhood during the filter operation, and it depends on to the certain conditions here. So for mathematical descriptions, or better way the steps of this particular type of the adaptive median filtering, we can consider few of the notations we shall go into the use of. So these are Z min to denote the minimum gray level into the neighborhood defined S of x comma y. Z max is the maximum gray level. Z med is the median gray level. Z xy is the gray level at the coordinate specified x comma y. S max is the maximum allowed size for the changes into the neighborhood dimension here. So when we have the adaptive type of the median filtering, we can set few of the steps here. So we can also represent them into the algorithmic form. So the algorithmic representation of this particular process can be better explained with the two levels. First of all, the level A, where we obtain A1 by subtraction of Z minimum from the Z median, whereas A2 is subtraction of Z maximum from Z median. If we have A1 greater than 0 and A2 less than 0, we have to go to the another level we are going to describe. Elsewise, we have to increase the window size, and if the window size is less than that of the maximum allowed level, we have to keep it increasing till we achieve that particular one. So else we have to give the output by this particular process to be the Z median here. So the level B is having B1 computed as the subtraction of Z minimum from the Z xy. B2 is subtraction of the Z maximum from Z xy. If B1 is greater than 0 and B2 is less than 0, we have to provide the output Z xy. Otherwise, the output is Z median here. So these are the else condition for which the adaptiveness is not there. It will be just the result of the median type of the filtering here. So there are the three main purposes to have such the algorithmic type of this particular adaptive median filter. So these purposes we shall discuss and conclude to see the visualization effect of this particular type of the filtering here. So the main purposes are: the first one, to remove the salt and pepper noise, also known by the impulse noise. Secondly, to provide the smoothing of the other noise that may not be the impulsive type. And lastly, to reduce the distortion, such as excessive thinning or thickening of the object boundaries here. So now, every time the algorithm that just now we have seen will be operating and generating a certain value, the window that we have defined or the neighborhood that we have defined as we have represented capital S suffix xy, it has to be moved to the next location into the image. I have already made it clear that we have to start at the top left and then we have to go into the right direction and then the downwards row by row here. So the algorithm, then it has to be reinitiated and is to be applied to the pixels into the new location every time. So this process is very rigorous. It will take a time here. So that is why one point I have already mentioned, that the superiority into the resultant values we obtain with the increase of the complexity of the algorithm or the filtering process here. So here we can have a concluding remark that the median value can be updated iteratively using only the new pixels, so therefore reducing the computational overload here. So finally, the example to see the visualization effect of having this particular adaptive median filtering operated onto the noise affected image. So here we have the three images. The first image is corrupted by the pepper and salt noise. The probabilities are 0.25. Then when such an input image is filtered by the median filter, simply a median filter, not that of the adaptive type, we get the resultant that is shown at the middle. And when it is the median filtering of the adaptive type, you get the resultant visualized into the third portion here. So adaptive median filtering is here preserving the sharpness and most of the information or the details of the image, for example the connector figures here. So you can compare this particular portion where the horizontal like structure, it is quite difficult to judge here properly, whereas it is quite clear by using the adaptive type of the median filtering. So here we have obtained the corresponding result. So this was our topic, the spatial filtering for image restoration here. So the filtering processes for the image restoration, those work into the spatial domain only we have considered. As like there are certain filtering processes, those take the help of frequency domain. So a direct transformation and the inverse transformation is to be made into the use. So accordingly we have also the frequency domain filtering methods for achieving the image restoration here. So these details you can see onto our platform, those are available, and by the next session we shall see the details of the RGB color model. So up till now we had been learning the various image processing techniques associated to that of the binary image and especially the gray level image. Here we are getting shifted to the color images, which is basically a stack of the red, green and blue. So the three planes are stacked together, so that is why we have the increase into the third dimension. So the image will not be a only two-dimensional signal but a three-dimensional signal.